Thank you, Ben. Thanks, Rupert, for the nice introduction to the problem. And now let's gonna talk a bit about DSLs, a very general introduction, and to give some already hints in the direction of why or how DSLs can actually help to address this performance and performance portability problem. But of course, there are always trade-offs. But let's gonna start talking about what is a domain-specific language. People might still not be familiar with the concept of a DSL, that is domain-specific language, that does not only appear in scientific computing, but we are gonna, of course, focus more on scientific computing at the beginning and then later on weather and climate actually applications. But let's gonna review just the very general concept, right? So imagine we are in scientific computing, one of the operations that happen is linear algebra, and one of the operations we could do is matrix transpositions. So how would we implement a matrix transposition in any general purpose programming language? It doesn't matter if it's C, Fortran, Java, it's very similar in all of them. All of them exposes a way or gives you a way to implement data layouts for matrices, and this is the example that we see here. The matrix is called M, and it has two dimensions that we name I and J, but this is your convention. And it's going to be, again, very similar how you code these in different programming languages. They're very general. You can do anything. Since you can do anything, they are Turing complete. You can, for sure, solve the problem of a matrix transposition. So how you go about it is, well, typically you iterate over the entire matrix. That means nested loops, two loops, I and J, over the row and the columns. And then you need to do this. You need to permute, basically, the elements across the diagonal of the matrix. Everyone would understand that. Now, there are some problems with these implementations. First of all, of course, this is a very simple example. If you would imagine more complex algorithms, it's actually very easy to introduce errors in here. You can't switch some of the indices, make a mistake between I and J. You can introduce parallelization problems. There are many problems simply because of the fact that everything is explicit. You can incur, for example, in a loop bound error. What if the size of the matrix that was allocated was not n, but it was actually less than n? Then it will typically generate an out of bounds. So these are the trade-offs between general purpose language. They allow you to do anything. At the same time, they are not the most concise way of expressing specific problems, and they are not the safest in many occasions. All right, so imagine then that you want to actually solve that problem. Then you could imagine if your problem is just focusing on matrix transpositions, then you can design a language that only does that operation and express that with a simple keyword. And the very good example now is looking at MATLAB. MATLAB is actually focusing a lot of the language into linear algebra. That's why doing the transpose in MATLAB is so elegant, it's so simple. There are very few mistakes or no mistakes at all that you can do here. This is the mathematical definition of a transposition. If you write here on the left-hand side, A equal B transpose, nothing can go wrong. If you do it with the implementation of the right-hand side, then you better right ahead, implement some testing, run some actual examples to verify that this is actually a transposition and take care of the corner cases that may appear. So this is the general concept of a domain-specific language. A DSL is nothing else but a programming language, but it's specific to a domain. You can, on the other side, you cannot solve all the problems that you could solve with C. You cannot have recursion, for example, in this MATLAB language of matrices, and you cannot have many other things that you could do in C. But the syntax that you obtain is very concise for the problem. So you bring the abstraction higher, and then you also at the same time hide many details of the implementation and the hardware. Something I still didn't mention is what happened with an efficient implementation of the right-hand side in C matrix transposition. Is not efficient. We need to take care of details like vectorization. We need to take care of details like parallelization, since we want to run this in multi-core machines or on GPUs. And this implementation completely lacks this capability. While on the left-hand side, you could assume that the compiler, MATLAB, or your DSL compiler should take care of these efficient implementations and these parallelizations. So this is the main advantage. The main limitation is, of course, the DSL is by construction limited. You cannot do anything. But it's well addressing the problem that was exposed by Rupert for before about the portability and performance portability of our weather and climate model. So now let's gonna talk about our domain. Things are different. We are not doing just simply matrix transpositions. So to explain a bit the process and the problem, I like really this slide coming from Willem de Koning describing the whole process from the physics, where the domain scientists are understanding the physical processes that happen in the atmosphere, and also the interactions with the soil and so on. And from there, they derive the mathematical description of the problem. So this is math, this is typically in equations. Then after this mathematical description, since what we get in these equations are PDEs, they normally get discretized. One needs to choose a discretization method, find the volumes, find the elements, find the differences. Well, we need to choose a grid and so on. And then we would go into the layer of the algorithm development. And for a particular operator, like a divergence or a gradient, this would end up in a particular algorithm that would solve in a discretized manner, so with some errors, of course, introduced by the discretization, but would solve to an approximation the problem described in the mathematical description. I'm not sure if people can see the mouse, but I'm trying to hover where I am in the box of the algorithm development. And then in an ideal world where we'd have DSLs or this abstraction, we could already use a language. Ideally, we could imagine that we could describe this algorithm in a language that is very concise and only exposes concepts needed to describe this algorithm and nothing else, as I was, for example, showing before the example on the matrix transposition using MATLAB. Because adding more keywords, adding more concepts, low level, hinders the purpose of readability, but also at the same time is more error prone, as I was explaining. And what happens below that language is actually you have all the other details needed, necessary in order to run efficiently. You need to, if you're running on a globe, then you need to create a mesh. The way the indexing is ordered in that mesh is actually very relevant for performance. Then it to take care of the details of the parallelization. We have many parallel models for different type of architectures. This is also what it was described before, GPUs, CPUs, and we have different programming models. And finally, you could even go down the level of the hardware specific instructions. So this is the whole concept of a separation of concerns. And one could solve separation of concerns in different ways. DSLs is just one. At the moment, we are only talking about the benefit of this separation of concerns would bring into our weather and climate models. So let's gonna start with a very simple or concrete example from these equations that I was showing here above. There are many operators and of course nabla, but it's divergences, gradients, chords. Let's gonna take the gradient, right? The gradient on a scalar that will create a vector. This is an example of an implementation in Fortran if you want to make it efficient. I won't go into the details. They will be presented through the training courses later on so that you can better understand why do we need to do all this? Why do we need so much Fortran code around in order to code something that performs well and that is correct? But believe me that all this is actually needed, especially when you need to target multiple architectures. That was actually the approach that we needed if we want to go to these pre-ESA scales and very set of diverse machines. So just to highlight that actually the interesting bit, what we really need is this. This is our main computation that we can read. The gradient is just the difference between two neighbors of the psi or f field, and just divided by the length or the distance between the two neighbors. That's all the information that we need. And we need to, nevertheless, in this implementation, take care of all this code, which is complex, and it will require quite a lot of maintenance. This is what is really hindering in the current models, the scientific development, and where DSLs can propose a solution. And again, going back to this picture, the solution lies on the problem again here is that there's only one layer. The implementation layer in the current existing models is dealing with everything. It's dealing with a particular solution to the discretization problem, is dealing with optimization, is dealing with multiple machines. So this implementation is dealing with all the boxes in here. And the typical solution in engineering is decouple functionality, modularize it, and decouple or find different solutions for for different type of problems. And this would be the proposal here that DSLs tackle, right? Like for example, a DSL could abstract different backends that are targeting different architectures, and we don't need to mix and mangle solutions for GPUs and solutions for CPUs within the same model, so within your science. All right, but the question now is, how do we do that? That's probably the holy grail question. How do we separate science from these complex implementations? How do we take just only this useful information, neglecting all the rest that I was arguing that is nevertheless needed if you want to run efficiently on the exascale computers? Because that's our goal in the end. We don't want to run on a laptop and slow, but we want to run on high performance systems. Okay, then there are different options, and maybe there are more. So I'm just summarizing probably from our experience what could solve that problem. So one would be to simply rely on compilers. That means a vendor. Wait until a vendor comes with a model that can solve these type of equations coming from PDEs with a language that is not going to be Fortran, C, or Java. It's just going to be a language for weather codes, or if you like, for PDEs. However, this is a very unrealistic option. It didn't happen so far, and vendors are, of course, covering or interested in covering a large market, and focusing simply on the problem of weather and climate is not going to provide enough enough momentum, right, so that they can find a business model out of this. And it's actually a complex thing to do, to develop in a specific language. But certainly that would be an option. If that would happen, that would be best, because this is the role also of the industry, to provide compilers that can compile weather codes and not necessarily using general purpose languages. Another option is to use general purpose, not languages, but programming models. And a programming model is something that it can work on top of an existing programming language, like for example, OpenCL, or for example, Cocos that is implemented embedded in C++, or they are close at least to an existing programming language. You are not starting from scratch. The advantage of these general purpose programming models is that they are able in principle to tackle different machines. So we could implement a single source code for our model, and at the same time with OpenCL we could, for example, execute on different type of GPUs, AMD and NVIDIA GPUs. While if you use CUDA, then you will only be able to use to run it on NVIDIA GPUs. So certainly it's an interesting option. It provides portability or more portability than others, but it still is complex, and they provide low-level implementations. So it's not solving the problem that is derived from the fact that your implementation in the end is quite technical and is quite low level, and it contains a parallelization underneath and so on. So you need to describe the parallelization in a very concise manner still, but the problem is still there. The final option is to use DSLs for weather and climate. And this is what this training is about. So I will not disclose all the details. Of course, you will learn about that during the week. It was just this introduction is to give you an idea of what is the use of DSLs, the importance of DSLs for our community. Again, as I always say, it's a trade-off. So there is also a caveat. The caveat is the community needs to agree on a DSL language, because one could develop 20 languages or one per model, and that would not be ideal because the development cost is actually high. And the community needs to develop the compilers, since the vendors seems that they are not going to provide those compilers for us. Anyhow, this is what we are developing in the context of projects like Escape, ESiWACE, and in the, sorry. Okay, let me go to now the what type of DSLs, right? So I was presenting here that we are in the training course, we are going to go through these two main ones that we are using in ESiWACE. And now let's talk a little bit about why are they different, or why do we have actually different type of DSLs? Not only different DSLs, but different type of DSLs. It's simply because we have two options. If you want to reduce all the implementation details as we were describing before, and only have a concise expression of the gradient, you have two options. One is to bring the abstraction higher. That means, again, to provide a new syntax, completely new language with only keywords that support what you need in order to encode that new concept. You will see through the course several times this type of syntax is coming from dusk and dawn that describes the gradient as a reduction, and a reduction is an iteration over neighbor grid points in your mesh. Doesn't matter the details, right? Somehow I'm describing it, but we will learn about it later on. But what it matters is that here there are no for or do loops. There are no loops at all. There are no memory patterns. We don't know the memory indexing. We don't know if these are 3D fields, where is in memory the vertical layer, is innermost or outermost. There are no indices of an iteration space. You can also not go out of bounds because they are not described in this language. And there is no parallelization at all. This is not part of the language. So this is one option to bring the abstractions higher. You provide safety and a very concise way of expressing it. It's also very limited, of course. Then you cannot do other type of operations than the ones that are supported here. The other approach is to use low abstractions, and that means let's gonna continue supporting existing programming languages like Fortran. But what we have to do is to limit the functionality supported. We are not gonna support recursion, while loops, or certain operations because they are not understood by our DSL compiler. But still, we could understand um, this type of computations where we have triple nested loops. This is a tracer gradient coming from NEMO. And the main idea is that we are not providing a new language and forcing the community to rewrite entirely everything into this new language. We could still continue operating with existing models. And the difference is that now we need a DSL compiler that parses this. You don't rely on general purpose compiler, but actually you provide a DSL compiler that will parse this and understand what you are doing and provide then the different backend implementations. I hope this is clear, but nevertheless, it's only an introduction, so we'll understand and learn more about this later on. That doesn't mean the fact that here we are in low abstractions and operating with Fortran, that it looks like we are going to support all the Fortran or existing models, because again, the functionality has to be very limited. And for example, we could not support parallelization details or blocking implementation details and things like that. We would assume that we operate on very naive Fortran existing implementations. And the typical example you will learn about is NEMO. Anyhow, we have these two types of approaches or DSLs. One where we bring the abstraction higher, the other one is where we work with existing low abstractions using Fortran. And to give or to put things in context, Dusk and Dawn, it falls in the first category, and Cyclone actually has two modes. It can operate with high abstractions, so providing a DSL language with keywords, and it can also parse and interpret existing code with those limitations. And the other difference is that Dusk and Dawn is Pythonic, is more Pythonic, the language, and Cyclone is mostly focusing on Fortran with the idea of integrating existing codes that are, as of today, they are in Fortran. Very good. Check it out on the time. When we go into higher abstractions, it's useful probably to give a little bit of historic view on it. It's not a DSL that has been developed in the ESiWACE project only in the last year or 2 years. There is really a long history. Developing these DSLs costs quite some funding, and it requires actually quite some time to really understand all the patterns, to put some prototypes in place, to bring some models in production, and then we are learning on the go what is actually needed. They are really long-term goals. So as I was saying, Dusk and Dawn is not starting from scratch. In Meteos, we put already the grid tools. There is another DSL version of the Cosmos Dynamical Core in production in 2016. And this is what you can see. I'm putting some examples of a Laplace. In this case, we are operating on a lat long world. And the Laplace is typically this Jacobian stencil. Is a very common one to explain how DSLs operate, because it's simple enough. It doesn't combine multiple operators and so on. And it has been a huge, actually, a huge success story, because it has been the first time that one could put DSLs into operations. And this makes a major difference. I mean, there are many DSLs out there, but putting something in operations means that you are complete, that you support everything, that you can operate, that you can maintain, and that you obtain actually very good performance, or better performance than with other models. So this was a success of it. Still, it was an early generation of DSLs, and there are some caveats, as we can see here, and that's why I'm putting this picture here. It's very much C++-like. It contains templates of C++, like this type name, evaluation, has keywords like static, void. These, I would say, they are not keywords of a language needed for expressing PDs. Static and void is just simply, or struct, they are simply keywords coming from C++. And it's because of the fact that this DSL was embedded in C++ using template metaprogramming. Finally, there was a way of combining or composing multiple stencils that allows to increase the data locality, and it was an optimization that the scientists could do. But this actually would also require that the scientists know about how to compose these stencils, and when you can do it and when it's not safe to do it. So as a summary, it still requires an HPC or a C++ expert. That's why it was not the end of the story. It was not like this is the final DSLs, and as I was saying, we are continuously evolving always those developments. So in this line, the new generation goes towards more Pythonic and high-level DSLs that abstract even more many of the details of this boilerplate code and the parallelization model. And we will learn about this also later through the course. This is a very simple idea where we start again from the gradient example. We encode it just like that in a Python-like, but it's not Python because it's not general Python, but the front end is in Python. And this is the syntax that we use to encode this mathematical expression. So we reduce over neighbors. We are computing on an edge, and then we reduce the neighbor cells of an edge. We will learn all these details, but it's basically a syntax that just simply says this is a gradient, difference between two neighbors divided by the length. And then you will need a compiler that is at the very end generating parallel complex implementations, optimizations, and you can have actually different backends. Very good. The other approach that you will hear about from Cyclone is to operate on existing codes rather than forcing the community or the model developer to rewrite using a new syntax and a new language that supports your patterns. So this is behind the idea that weather and climate models, it will take a while. First of all, one will need to be successful, very, very successful. Then the community will need to find a model for agreeing on one DSL and maintaining it in the long term and so on, until we can see that models are potentially being used or being put in production with these DSLs. So the approach of Cyclone is quite interesting because it allows during this transition to operate on existing weather and climate models that are under the continuous development and that are written today in Fortran. At the same time, it's not that we can pay the price of, say, as I was explaining, developing these DSLs is going to take a long time. What we are bringing here again is a development stage of the tools and the DSLs, and it will take a few more years until we can say we are ready for production. So we cannot stop the development of the existing code and the model, say let's gonna take a gap of 10 years, and then once the DSLs are ready, we continue doing model development. That will not work. And this is the interesting approach here that Cyclone gives us, because as we develop still the models, we can operate on using these DSLs, and we can enable the existing models or some of the existing models into the process scale systems. Anyhow, we can summarize this as an approach that is an evolution rather than a revolution. Everything has advantages and disadvantages, as I was explaining. And here in this training course, we are giving you the two possibilities. So if we summarize a bit the two approaches, probably Dawn would be bringing the abstraction higher, covering part of the algorithm, while Cyclone can also work. It works within a specific implementation, and therefore the abstraction is a little bit lower. This is the very same example I was showing before, just to explain how the Cyclone compiler in this mode works. Again, we start with the Fortran implementation, no parallelization, no complex implementation in here, no caching or things like that, because the compiler would not know how to deal with it. But as far as we restrict ourselves to triple nested loops, because we have 3D fields and operations that are doing stencil accesses like I plus 1 and j minus 1 and so on. And then again, this is the example of the gradient that we could read, and we could read still here, even though there are loops and implementation details, we can read because there are no many other things. And so the Cyclone provides a parser of this code, a Fortran frontend. It will go into the DSL compiler, and this gets translated into an intermediate representation. And rather than passing this to GFortran or GCC, basically there is a compiler operates on this intermediate representation, and now it knows what to do. It can identify patterns. It can identify that you have an stencil, horizontal stencil operation, or a vertical solver, or things like that. And then at the very end, you have different backends that are in charge of from this intermediate representation to generate an efficient parallel program. That's more or less the way it works. And with that, I hope I have given you an overview of the two DSLs that we are going to learn through the week, and mostly what are the differences between the two of them. But hopefully you are now a bit convinced that this is an interesting path to approach the performance and performance portability problem. Anyhow, it's only one of the solutions, as I was explaining, to the separation of concerns. It's only one way of dealing with it, but a very promising one. And what we will learn during this week is again how they actually work, and hopefully you will learn more about the potential. At the same time, you will also learn the details of things that can be improved, and we're always interested in hearing your feedback. And with that, that was my part.